Let's look at another application of our mass flow problems, and this one's going to be for compressors and pumps. And basically what we have when we have compressors and pumps is we're going to have work that's being done on substances that are flowing through them, and the state of the substance will change. And for the substance, if we have gas, we say we have a compressor. If we have liquid, we're going to have a pump. Alright, and if you want to know how the compressors and pumps actually work, that will be a different course. We're just going to apply our energy balance equation to compressors and pumps here. Alright, so here let's look at what we've got. If you think about a compressor or a pump, the system itself is not going to be able to change the state of the substance by itself. It's going to require a WCV dot that is less than 0. So that means you're going to have some sort of external power supply, something to make the compressor change the pressure, for example. All right, so we're going to have a negative WCV dot in order to operate a compressor or a pump. Now let's go over an example. We're going to have refrigerant, and it's going to enter an insulated compressor that's operating at steady state. That refrigerant enters as a saturated vapor at a temperature of negative 20 degrees Celsius. Mass flow rate is 1.2 kilograms per second, and the refrigerant then exits at a pressure of 7 bar and a temperature of 70 degrees Celsius. Notice there that the temperature increased. Now we're going to ignore kinetic and potential energy effects. We will find the volumetric flow rates at the inlet and the exit. We're also going to find the power input to the compressor in units of kilowatts. Keywords, let's find the keywords. First of all, we've got insulated. Next, we've got steady state. Tells us it enters as a saturated vapor. And we want to ignore these two things. And we're going to find volumetric flow rate and power input. All right, so main things we need here: insulated, steady state, saturated vapor. Now, if we want to find the volumetric flow rate, remember what that is. Volumetric flow rate is A times V. We need an equation that has A times V in it. M dot is A times V over V. So let's use this equation. Okay, so I'm going to draw a simple picture. Let's just say we have something that looks like this. We've got the refrigerant coming in here. The temperature is negative 20. We've got M dot, which is 1.2 kilograms per second. This is our inlet. Our exit, we've got a pressure of 7 bar, and we've got a temperature of 70 degrees Celsius. Alright, so now we've got that. Now if we use this equation, let's go ahead and solve for AV. And let's do this at the inlet. So at the inlet, we're going to have M1 dot V1 equals A1 V1, where this V is velocity. Alright, now for refrigerant, we're going to use the table A10. And we need the table because we have to have this specific volume. So V1, we go to table A10. One more thing to notice before you go to the table, notice it says it enters as a saturated vapor. So this is telling you that you need to use the saturated table. All right, and this is the one for refrigerant 134A. So this is our liquid vapor table. That's the one we will use. We need to find V1. We have our temperature, negative 20, and we're at saturated vapor. So we're going to go all the way over to right here. This is the VG. Notice this is saturated vapor. So we have 0.1464. So V1 is going to be 0.1464, that's cubic meters per kilogram. Now we have that. Now we already have M1 dot, that was given. We have V1. We can plug that into this equation and solve for volumetric flow rate. So 1.2 kilograms per second times V1, so 0.1464 cubic meters per kilogram. That is going to equal A1 V1. Notice your units will end up being cubic meters per second. That's what we want. So A1 V1 is 0.1757 cubic meters per second. That's our volumetric flow rate at the inlet. So essentially what that says is 0.1757 cubic meters of refrigerant is entering this area right here per second. Now we want to find the same thing at the exit. So let's look at the exit. Now at the exit we have a pressure of 7 bar and the temperature is given. For this one, let's figure out what we've got. We need to figure out if we need to use the saturated table, superheated vapor, what is it? So let's draw this. Our pressure is 7 bar, so let's put that on here. At 7 bar, what we have, this is our pressure table here. 7 bar, what we're going to have is a saturation temperature of 26.72 degrees Celsius. Now we said we're at 70, so we're way up here somewhere. Now obviously in order for this to intersect with this pressure right here, this means we are superheated vapor. Alright, so now we got that figured out. Then you're going to go to the superheated vapor table for the refrigerant, and you'll look up your combination of pressure and temperature. We are at 7 bar and a temperature of 70. So that's going to be this table right here. Here's 7 bar, here is 70. This first number right here is specific volume. So 0.03634. That's the number we will need. Let's write that number down. This is cubic meters per kilogram. And that was from table A12. If you're following along with the same tables that I have. Now we have this. We're going to use that same equation that we started with up in this part when we did the inlet. Now let's do M2 dot times V2 equals A2 V2. Just need to plug in your numbers. So we have 1.2 kilograms per second, because remember this is steady state, so M dot 1 is going to equal M dot 2. And here we're going to have 0.03634 cubic meters per kilogram, and that's going to equal A2 V2. Multiply these out. Notice kilograms goes away. You get a volumetric flow rate for the exit of 0.0436 cubic meters per second. All right. So at the exit, we've got 0.0436 cubic meters of refrigerant exiting right here at our exit point of that compressor. Now we have one more part to do. And this last part, we need to find the power input to the compressor. Now remember, in order for a compressor to work, you have to have this thing plugged in. Something's got to be causing all of this to happen. So we need to figure out what the power input is going to be. Let's work on that. For this part, we're going to use our energy balance equation. It's steady state. So the time rate of change of total energy in your control volume is going to go to 0. we've got our Q dot term minus W dot plus M dot times H1 minus H2. I left off the kinetic and potential terms because it said to ignore those. Remember, M1 equals M2, M1 dot, I mean, equals M2 dot. Both of those will equal M dot. This leaves this equation. Now, do we have a Q dot? If you look back at the problem, what does the problem say? The problem states that it's insulated. So if you see insulated, that's usually going to mean that we can ignore any sort of energy transfer due to heat. So let's let this go to 0. Now we're looking for this. This is what we're trying to find, W dot. We know what M dot is. We need to find H1, H2. These are going to come from the tables. You're going to use the same tables we used to find specific volume. So A10 will be used to find H1. So that will be 235.31. That's kilojoules per kilogram. Table A12 will give you H2, which is 307.01 kilojoules per kilogram. We just plug these numbers in, and then we will be ready to solve for this. 0 is going to be negative W dot plus 1.2 kilograms per second times 235.31 minus 307.01. That's kilojoules per kilogram. Now we've got that. Notice kilogram goes away here. Let's go ahead and multiply these numbers together, and then we'll look at our units. Bring W dot over. W dot then is going to be negative 86.04. That's kilojoules per second. We want units of kilowatts. The conversion for that is 1 kilowatt per 1 kilojoule per second. So these will cancel that. That leaves us with kilowatts. So W dot is going to be negative 86.04 kilowatts. So that is the power input that is required in order to make that process happen. All right, and remember this sign right here, that's negative. Remember, if you have a negative, that indicates you've got a power input. If it's positive, your system is generating power to send out. So let's put power input here. Hope you like that one. I will see y'all in the next video for heat exchangers. See ya.